Hello everyone, I'm Paul and today we're solving problem 1611, minimum 1-bit operations to make integers 0. This is a hard one, but I think this becomes much easier with visualization, so let's go from the basics to the solution. We are given an integer n and we have to transform this into 0 using these two operations any number of times. For the first operation, we can change the rightmost bit. So if this is the binary number, this is the rightmost bit, this is position 0. For the second operation, we can change any bit only if the bit that's right next to this one to the right is a 1, and then every other bit to the right is 0. Okay? So in this case, we could change this bit. So let's go from the basics. Let's say that n is 3. This is the base 10 representation of this number. If we want to transform this into binary, meaning base 2, we need 1 2 to the power of 1 and 1 2 to the power of 0. So this is the binary representation of 3. And just to be clear, remember that this is 2 to the power of 0, this is 2 to the power of 1, and so on. So we need 1 2 to the power of 1 plus 1 2 to the power of 0. And 2 plus 1 is 3. So for this example, the result is initially 0. First, we can use operation number 2. We transform this into 0, and we can do this because we have a 1 to the right, and then we don't have anything. So here we have one operation, this is 1. And then we can use operation number 1 to transform this into 0. And after 2 operations, we get number 0, so we return 2. Now let's say that we are given some power of 2. Let's say that we are given number 8. The binary representation of this is 1, 0, 0, 0. So we need 1 2 to the power of 3 to get this base 10 representation. And now the question is, how many operations do we need as a minimum to transform this into 0? And you can play around with this, but the answer is the following. We can use operation number 1, then operation number 2, then operation number 1, then 2, then 1, then 2, then 1, then 2. And in case you didn't notice, we are alternating operations. First we use operation 1, then operation 2, or 1, or 2, and so on. This is the right pattern to get the minimum number of operations to transform this bit into 0. And here we have 1, 2, 3, 4, 5, 6, 7, 8 operations. So this bit requires 8 operations. And now we have this number, which is another power of 2. We have 2 to the power of 2. So now the question is, how many operations do we need to transform this into 0? Well, first we can use operation number 1 and get 1, 0, 1, then 2, then 1, then 2. And that's it. So we need 4 operations, and this is the new number, which is also a power of 2. Now the same question here, how many operations do we need to transform this into 0? Well, we start with operation number 1 and get this, then we use operation number 2 and get this. And that's it. Here we need 2 operations, and this is the new power of 2. Finally, we have this, so we can use operation number 1 to transform this to 0. And this is the key observation of this problem. We need 8 operations to transform this bit into 0, meaning 2 to the power of 3 operations, which corresponds to 2 to the power of the current position. This is position number 3. Then we get this number and need 4 operations to transform this bit into 0, meaning 2 to the power of 2 operations, meaning 2 to the power of the current position. Okay, so then we get this number and we need 2 to the power of 1 operations, meaning 2 operations. Then we get this and we need 2 to the power of 0 operations. So if n is 8, how many operations do we need in total to get 0? Well, we need 8 plus 4 plus 2 plus 1 operations, meaning 12, 14, 15. So in this case, we return 15. Now remember the basics of binary numbers. 15 in binary is 1, 1, 1, 1, meaning we use 1 to the power of 3 plus 1 to the power of 2 plus 1 to the power of 1 plus 1 to the power of 0. This is, in total is 15. So instead of doing all of this, we can take the position of the last set bit, meaning 3 in this case, and do 2 to the power of that position plus 1 minus 1. And here 3 plus 1 is 4, so this is as if we do 2 to the power of 4, and 2 to the power of 4 is 16. So this is the binary representation of 16 in base 10. And what happens if we subtract 1 from here? Well, we get 15, meaning this in binary. So by doing this, we get this binary number. This has the same amount of positions as the original number, 2 to the power of 3. And every bit here is set. Every bit is 1. This is exactly what we want. This is exactly the result. So if n is 8 or any power of 2, we can just use this formula and get the result. Now what if n is not a power of 2? Let's say that n is 10. This is the binary representation of 10. We need 1 2 to the power of 3, meaning 8, plus 1 2 to the power of 1, meaning 2. So the question is, how many operations do we need as a minimum to transform this into 0? We know how to get the result for any power of 2, so we can split this into two subproblems. First, we get the result of this binary number. We only consider the leftmost bit, so we have this, meaning 8 in base 10, and we already know that the result for this is 15. We can also get the result of this subproblem, this power of 2, and we know that it's 2 to the power of 1 plus 2 to the power of 0. So the result for this is 3. And now we can take this and subtract this, so we return 15 minus 3, meaning 12. So the result for this number is 12. And this makes sense because if we only had one set bit here, we would need 15 operations, but given that we have another set bit, we need less operations, so this makes sense. Now, how many operations do we need to subtract from here? Well, the corresponding operations for 2 to the power of 1, okay? So that's why we subtract this. So as you can see, we can solve this recursively. First, we get the result for the leftmost set bit, and then we recursively subtract the corresponding operations for the next set bits. In this case, we only subtract 3. I hope this is clear now, and with this in mind, let's go with the code and hopefully you will get the idea. Here we need to implement a recursion, and remember that in any recursion we need a base case. And here the base case is if n is 0, return 0. Now we need to find the position of the last set bit. This is initially 0, and there are many ways to do this. Here I will show you 3. For the first one, we can say current is n, and while current is different from 0, we remove the rightmost bit. So this means current divided equal 2, and we add 1 to last. Now, this will give us the total amount of bits, but we need the position of the last set bit, which is the total amount of bits minus 1. Now, remember our formula. Finally, we need to return 2 to the power of last plus 1 minus 1, okay? And here we need to subtract the different scenarios for the next set bits. This is self dot this function, and here we need to use the current number without the leftmost set bit. remember the approach. And how can we remove the leftmost set bit? Well, we can do n bitwise XOR 1 left shift last, okay? Or 2 to the power of last, which is exactly the same. So let's submit this. As you can see, this works and it's very efficient. Here time complexity will be log n for the amount of operations for the leftmost set bit, meaning the power of 2 taking only the leftmost set bit, times the amount of operations that we can have to the right, meaning the next powers of 2 that we can have, meaning log n. So overall time complexity is log n squared, and space complexity is big O of log n. Now, here, instead of doing this, we can say last is 0, and we start from 1. Here we are starting from position 0, and we are moving from right to left, okay? So now we say while current is smaller or equal to n, current times equal 2 and last plus equal 1. And this will also give us the amount of bits, but we need the position of the last set bit. So here we need to subtract 1 from last. Sorry. And this should give us the same result. Let's submit this. As you can see, this works and it's basically the same, but we are starting from 1, meaning 2 to the power of 0. Now we have another way to get the position of the last set bit, which is we can use a Python function bit length, and this will give us the amount of bits, but once again we need to subtract 1 because we are trying to get the position of the last set bit. So let's submit this. As you can see, this works and it's more efficient than these two solutions because this method is based in C programming language. That's why it's much faster. So with this, it's as if we are solving this in roughly big O of log n time complexity, okay? So this is it for this problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.